Welcome to the deep dive. We cut through the noise to find the real insights you need. Today we're tackling something that honestly has always felt like pure science fiction: teleportation. But hold on, forget beaming people across space. We're talking about a huge leap in quantum teleportation. We've gone through the reports, the research, the news, all the source material to pull out what really matters for you. So, our mission today: demystify quantum teleportation, what it actually is. Then unpack a specific, very recent breakthrough, and finally explore what this really means for, well, for your digital life, for the future of how we communicate. And here's the hook, the core thing. In 2024, researchers didn't just teleport light in some sterile lab environment. They did it over live internet cables. Yeah, the exact ones carrying your emails, your streaming, everything, right now.
Exactly, and that's really why this is such a game changer. For so long, quantum teleportation was, fascinating, but mostly a lab curiosity. This specific breakthrough, though, it really pushes it towards practical possibility, a critical state. It's a concrete move towards a functional quantum internet, and the credit goes to the researchers at Northwestern University. What's so powerful, I think, is how it tackles that big question. How do we actually integrate this amazing science into the infrastructure we already have?
Okay, right. So let's unpack this then, because for decades, this stuff was pure theory, beautiful maths, but seemed impossible. Then you start hearing about qubits, entanglement, Bell state measurements, all these pieces needed to unlock it. Can you break down these fundamental building blocks for us, maybe starting with the qubit itself?
Absolutely. So at its heart, quantum teleportation isn't about moving an actual particle from A to B. It's about transferring the state. Think of it like the specific properties, the identity of one quantum particle onto another particle somewhere else. The particle itself doesn't travel. It's more like perfectly copying all the unique details of one car onto an identical car far away, making that second car become the first one in terms of its state.
Okay, copying the state, not the thing itself. Got it.
Right, and to do that, you need basically three key ideas. First, qubits. Unlike a normal computer bit, which is just 0 or 1 off or on, a qubit is different. It can be 0 or 1 or kind of both at the same time. That's superposition and lets them hold way more information, crucial for quantum computing.
That superposition thing is always a bit mind-bending.
It is. And then there's entanglement. This is maybe even weirder. You link two particles, could be photons, electrons, whatever. They become connected. Their fates are intertwined no matter how far apart they are. Measure one, and you instantly know something about the other. Instantly influence it.
Like spooky action at a distance, as Einstein called it.
That's the one. It
That's
feels
not fun.
non-intuitive, but it's real, and it's essential here. Finally, you need the Bell state measurement. This is the clever part, the how-to.
Yeah.
You take the particle whose state you want to teleport, and you take one of your entangled particles. You perform a special measurement on both of them together. This measurement gives you a result, just normal classical information, like a few bits of data.
Okay.
You send that classical information through a normal channel, like an email or phone call, to the location of the other entangled particle. That classical information tells the person at the receiving end exactly what operation to perform on their entangled particle, to make it take on the exact state of the original particle you wanted to teleport.
Ah, I see. So the classical information is key to completing the process.
Absolutely critical. And this is why it doesn't violate relativity or allow faster than light communication. You still have to send that classical measurement result, and that message is limited by the speed of light.
Right. That's a really important clarification. No FTL travel here, folks. Okay, so those concepts are, well, they're complex. But seeing them in action is where it gets exciting. Which brings us back to Northwestern University. What did they actually do that was so different, so much more advanced than previous attempts? Why is it such a leap?
Yeah, this is where it gets really interesting. The Northwestern experiment, it really sets a new standard for integrating this into the real world. First, the distance, over 30 kilometers. That's pretty significant on its own.
30 kilometers, okay.
But the huge difference, the real breakthrough, was the medium. They used active commercial fiber-optic cables. Cables that were at the same time carrying normal internet traffic, your emails, my video calls, streaming data, all flowing alongside the quantum signals.
Wow. Okay, how did they even manage that? Wouldn't the signals interfere like crazy?
You'd think so, but they used a technique called wavelength multiplexing. It's actually pretty established in telecom. Essentially, they used different colors, different wavelengths of light for the quantum signal and the classical internet traffic. Think of it like giving the quantum data its own separate, invisible lane on the fiber highway, so they didn't bump into each other.
Clever. Like different radio stations using different frequencies.
Exactly that kind of principle.
Yeah.
So the quantum signal was carried by a single photon encoded with a qubit state.
Yeah.
And a classical channel on a different wavelength in the same fiber carried that Bell state measurement result needed to reconstruct the qubit at the other end.
And it worked, even with all the noise from normal internet traffic.
It worked remarkably well. They achieved high fidelity, meaning the reconstructed quantum state was very accurate, very close to the original, even with all that background noise. And the crucial takeaway here, the reason this is so big, they proved that our existing internet cables can potentially handle quantum data. This suggests we might not need to build a completely separate, incredibly expensive network just for quantum communication. We could leverage what's already there.
That potential for integration, that's huge. It lowers the barrier significantly. And looking back at the sources, it really highlights the jump. You mentioned earlier work, like IBM and NIST back in 2015. That was just a few kilometers, right? And purely in a lab setting, no other traffic.
Correct. Controlled conditions, no real-world interference.
Then the University of Geneva in 2019 pushed it further, maybe 10 kilometers, but that was on dark fiber.
Yeah, dark fiber, basically
Yeah.
unused cables, no commercial traffic running alongside. Still a step, but not the same challenge.
So Northwestern, hitting 30-plus kilometers on live, active internet lines, running classical and quantum together for the first time. That really does feel like a major hurdle cleared, validating that integration is possible. It's, yeah, a different league entirely.
It really is. It moves from, can we do this in principle, to, can we make this work in the real messy world?
Mm-hmm.
And the answer seems to be yes.
Okay, so the big question then, the so what, for everyone listening, what does this actually mean for you? How does this abstract science translate into things that might affect our lives?
Well, the ultimate goal that this kind of work feeds into is the quantum internet.
The quantum internet. Sounds impressive. What does that enable?
Imagine communication that is fundamentally secure, not just hard to hack, but provably unhackable because of the laws of quantum physics, using something called quantum key distribution, or QKD. If anyone tries to eavesdrop on the quantum channel, the very act of measuring disturbs the state, alerting the sender and receiver.
True tamper-proof communication.
Exactly. Think about secure voting, protecting financial data, government secrets, critical infrastructure control. It's a paradigm shift for security. It also enables distributed quantum computing. Imagine connecting multiple quantum computers, maybe across a city or even further, using entanglement. They can work together to solve problems far beyond what even today's biggest supercomputers can handle.
So connecting this bigger picture, it's about security and vastly increased computing power distributed securely.
Precisely. For national defense, scientific research, drug discovery, the possibilities are huge. But it's not just about communication and computing. Those are the big ones. Think about medicine. Quantum-enhanced sensors could lead to much higher precision in medical imaging, maybe catching diseases far earlier.
Okay, so diagnostics.
Yes. And finance. Imagine instant, quantum-secured financial transactions. No chance of interception or tampering during transit, protecting your bank details, market trades.
That would certainly change things in the financial world.
Definitely. And even AI. Training complex AI models takes enormous computing power. Quantum networks could allow faster training by distributing the load across multiple quantum nodes securely.
So it really touches almost every area where secure or high-performance information transfer is critical.
Pretty much. The potential applications span a vast range of fields.
It sounds incredibly promising. But as always with big breakthroughs, there must be challenges ahead, right? We're not getting a quantum internet tomorrow. What are the next big hurdles?
Oh, absolutely. This is a major step, but the road ahead still has significant obstacles. One major one is signal loss, or attenuation. Quantum states are incredibly fragile. Even in fiber optics, the signal weakens over distance. Northwestern used clever filtering, but for longer distances, especially global ones, we need much better quantum repeaters.
Repeaters. Like boosters for the quantum signal.
Sort of, yeah, but much more complex. They need to receive a faint quantum signal, store it, entangle it with another particle, and effectively teleport the state further down the line without destroying it. It's a huge engineering challenge.
Okay, repeaters. What else?
Quantum error correction. Just like digital data can get corrupted, quantum states can too, due to noise and decoherence. We have basic filtering now, but we need robust, fault-tolerant systems to detect and correct these errors automatically, especially in noisy real-world networks.
Makes sense. Building resilience into the system.
Exactly. Then there's scalability. We're talking citywide networks based on experiments like Northwestern's, scaling that up to national, then intercontinental levels. That's a massive leap in complexity and infrastructure.
From kilometers to thousands of kilometers.
Right. And finally, standards and protocols. Right now, different research groups might use slightly different methods or technologies. For a truly global quantum internet to work, everyone needs to agree on common standards, just like we did for the classical internet with things like TCP/IP. We need global coordination.
So repeaters, error correction, scaling, and standards. A lot to work on.
Definitely. But there is a roadmap emerging. People are thinking about the stages.
What does that look like? What's the timeline, roughly?
Well, in the near term, say the next 5 years, maybe up to 2030, we'll likely see more demonstrations like Northwestern's, expanding across larger city or even national networks, building those foundational links.
Yeah.
We also desperately need commercial-grade quantum routers and those repeaters we talked about. That's a key focus for R&D right now. And you'll probably see more pilot programs. Quantum secure communication for specific uses, like banking or government agencies, testing it in real applications.
Getting those early adopters on board.
Yeah, and that investment is critical. It drives the technology forward. It shows it's moving beyond just the lab.
And then further out, midterm.
Midterm, let's say 2030 to 2040, the vision gets bolder. That's where you might start seeing true interconnection of quantum computers, creating a sort of quantum cloud computing capability. We might see the emergence of hybrid ISPs, internet service providers, offering both classical and quantum connectivity. And to go global, overcoming the repeater challenge for undersea cables. People are seriously looking at using quantum satellites, using satellites to relay entangled photons across continents.
Quantum satellites. Okay, that definitely feels futuristic, but it follows the logic.
It tackles the distance problem in a different way.
So wrapping this up then, the big takeaway from this deep dive seems to be that quantum teleportation. It's not science fiction anymore. It's real, they've shown it can be repeated reliably, it's becoming scalable, and crucially, it works on the infrastructure we already have.
Precisely. The implications are just enormous. For cybersecurity, for the future of computing, for telecommunications, it's hard to overstate. This research, like the Northwestern experiment, really does set the stage for what could become the world's first quantum internet. And that would be a truly transformative moment in how we handle information, maybe as big as the invention of the classical internet itself.
So here's something to think about until our next deep dive. Imagine a future where your most critical data, financial, personal, governmental, truly cannot be intercepted sneakily, or where immense computing power is shared securely across the globe through these unhackable quantum links. What other possibilities does that unlock that maybe we haven't even touched on today? And what new questions does it raise about information, privacy, and even power in that future?